We'll start with the homework. I think it was 35, 36, 37, 38. Okay. 35 says if milk has a specific gravity of 1.08, what is the pressure at the bottom of a can? 550 millimeters deep. So a metric problem. What does the 1.08 kind of mean? Specific gravity of 1.08. What's it mean? What does specific gravity do? What was this? What was the equation for specific gravity?
Specific weight.
Yep. Yep. Specific gravity equals the specific weight of something over the specific weight of water. Right? So what it is it's a comparison to water. So if the number is greater than 1, the fluid is thicker, more dense than water. If the number is less than 1, then it's lighter. So if you pour milk into water, would it float or would it sink? That's a good question. Yeah, it would sink. Yeah, it's got a greater specific gravity than water. All right, so that means that 1.08 is equal to the specific weight of milk over the specific weight of water. And what's the specific weight of water? 62.4, but this is a metric problem, right? So maybe we want to put in a metric number there. 9.81 newtons per meter cubed. And I actually just memorized it because it's the same as the gravitational constants, which is super weird, but I'm going with it. Right, so that will give us the specific weight of milk. We solve this equation by multiplying this across. We get the, I'm going to start writing it down here. Specific weight of milk is that times that. Since this is unitless, we just end up with this unit, N over meters cubed, 10.5948 newtons per meter cubed. Okay. Everyone good with that? Yeah, and so it's specific weight of water would be 9.81. Milk has 10.59 newtons per meter cubed, so it's heavier because this is weight, right? So this thing is heavier than water for the same amount of volume. It's going to sink. All right, so now we just need, what did they want to know? The pressure at the bottom? Yeah. What was the pressure equation for something underwater? Specific weight times H, just the depth. Yeah. So we know the specific weight now, 10.5948 newtons per meter cubed. And how much depth do we have? 550 millimeters. How many meters is that? Yeah, just move the decimal 3 places, 0.550 meters. So our pressure would be 0.550 times 5.827, so 5.83. Newtons per meter squared, and what? There's There's a common name for newtons per meter squared, pascals. Same as a Pascal. And Pascal's the scientist who came up with it, so. The P in Pascal gets capitalized because it refers to somebody's name. 5.83 newtons per meter squared. It's a half a meter, like it's this, it's this deep of milk. So generated a little bit of pressure. It's not much. So when you're given something like the specific gravity, that means you're given the specific weight of the fluid. You just have to calculate it. Compare it to water and calculate it. Questions? Good. Good there? Good so far? All right, 36. Says the pressure in an unknown fluid at a depth of 4 feet is measured to be 1.82 psig. That's gauge pressure, 1.82. So I'm going to start writing this down. 1.82 psi gauge and a depth of 4 feet. Compute the specific gravity of the fluid. All right, what was the equation for specific gravity? Again, specific weight of unknown fluid over the specific weight of H2O. Right? Let me make sure I got all this. Yep, they want to know the specific gravity, SG. And we know H and we know P, right? So the pressure equation is what? Specific weight times H. And we know this and we know this. Yeah. We don't know this. But we can calculate it. 1.82 pounds per inch squared. So I turned PSI into the unit of pound per inch squared. Set it equal to the specific weight times H, 4 feet. We might want that in inches, 48 inches. Gives us our specific weight of what? It's 1.82. 1.82. Do my algebra, so I'm going to divide by the 48. 0.0379. And that's going to be pounds per inch to the third. Because we take the inch over, right? When we divide this through, this divides down, makes that inches squared inches to the third. They didn't want specific weight, though. They wanted specific gravity. So then we just got to find the specific gravity, SG, equals that 0.0379 pounds per inch cubed over 62.4 pounds per foot cubed. So we have to be careful with those units. Specific gravity needs to be unitless, so this unit and this unit need to be the same, right? So we got to have a 12 to the third inches to the third over foot to the third conversion. That gives me pounds per feet cubed on top and pounds per feet cubed on the bottom. So a factor of 12 to the third times that number. 12. Is that divided by 62.4 by 1.05. And that's unitless. And what's that tell us? The specific gravity is 1.05. Yeah, it's heavier than water. Not much, but it is going to sink, which normally means it's going to mix, which is something that we're interested in fluid mechanics, is whether two fluids will mix or not. Like if they won't mix well, like oil and water, oil just sits on top, then mixing it is a problem if you want a good mixture between the two fluids. So we refer to this specific gravity thing quite a bit. And it also helps us with fluid transfer. Like if we're going to transfer a fluid, we probably know the base possibilities of transfer for water. We know all that information, horsepower and all that stuff. But now if we're going to transfer something that's twice as heavy as water, like mercury or something, then we're going to need a lot more power. All right, that was 36. Questions? Is that all good now that we walked through it? They're pretty simple formulas, right? But it gets complicated. Like the units, the unit becomes very complicated. You got to put those units in there and be diligent with it. I mean, I went back over here just to make sure they were actually asking for the specific gravity, because sometimes they'll ask for the specific density, right? Or the specific weight. And I'll be like, I'll get that confused with specific gravity and I'll start to find specific gravity when I don't need it. So yeah, the terminology and the units, the equations are not complicated. That's about as simple as it gets, 3 variables.
Yeah.
So it's just keeping it all straight. And this one's not complicated either, right? Specific gravity is just this comparison. But it's the terminology, specifics in both of them, right? Gravity and weight, and then the formulas and the units. Especially in the metric system when we're not that used to, pascals and newtons. It's just a strange unit. All right, 37. But this is what we're good at, us engineers. We're supposed to be good at this at least, right? Is those little details of units and those kind of things. 37, the pressure at the bottom of a tank of propyl? How do you say that? What is that? Propyl? Okay, I like that better than what I'm saying. Propyl alcohol. The pressure at the bottom of the tank of propyl alcohol is 25 degrees C. No, the pressure? Oh, at 25 degrees C must be maintained at 52.75 kPa. All right, I'm going to write this down. Pressure 52.75 kPa. What's the K stand for? Kilo. Yep, thousands of pascals. Correct. 25 degrees C. What depth of alcohol should be maintained? All right, so this 25 degrees C is just a distraction. Right? So that's good that they're starting to throw you some distractions, because the normal problem comes to you with a hell of a lot of distractions. That's for sure. All right, so we want to know H. So that's the other thing I encourage you to do, is try and use the variables that the book is using. Even though it said the depth of this is whatever, we know H is in the pressure equation. So call it H. Like I need H. They called it depth. That's great. But I need H because I know that P equals the specific weight times H, the depth. And what did they want to know? Specific gravity? No, specific. What depth? H. Okay, perfect. And we only have the pressure, correct? That's the only thing given. Yeah, so P's given. We don't know H. Uh-oh. I bet we can then look up. We probably have to look something up, don't we? Propyl. What's the specific gravity or the specific density of propyl alcohol?
Specifically in propyl alcohols, that's
7.87 kilonewtons per meter cubed. Where'd you get it? Okay. Anyone find it in the book? No? I wonder if it is in the book. All right, just bear with me here. Let's see what kind of appendixes we have. Properties of air, viscosity and temperature, properties of petroleum lubricating. We just want properties of properties of water, common liquids. Let's check that one. I don't know that propyl alcohol. Properties of common liquids. What'd you give for specific? 7.87? Boom, look at that. Google, friggin' stepping up. And kilonewtons per meter cube, perfect. So there is a table in the back, that's kind of nice. And those are some common fluids that I've never worked with, so that's even a better table than I would expect. Seawater's there. I don't know. There are, like, if you go into microchip, there are the most amazing fluids they use down there for all their different processes, like crazy fluids that I've never even heard of. So, yeah, I guess in those kind of settings. All right, perfect. Perfect. We're going to go with 7.87 kilonewtons per meter cubed. We want to know H, so we're going to use this formula. Now we know this, so we're just going to set it up. I'll set it up the way it is and then solve it. 75. So I can get rid of the K by moving the decimal point 3 places. Okay, so that's how I would deal with the K. Just get rid of it. So it's not 52, it's 52,000. And pascals, I know is a Newton per meter cubed, or squared, sorry. So that's the other one that you probably ought to just note because you use it a lot. A Newton equals, or a Pascal equals a Newton per meter squared. Okay, and this is equal to the specific weight, 7.87 kilonewtons per meter third. I could have got rid of the kilonewtons too. Here, I'll do that. By the same method of moving the decimal point 3 places. So 1, 2, 3, we'll turn that into a comma. And now it's newtons per meter cubed. And then H. So just working to get those units similar in the beginning is helpful. You had kilonewtons on both sides, so you probably didn't have to do that, right? I just didn't notice it. So since you had the K here and you had the K here, those would have crossed. So what I just did was unnecessary. But I guess it's how my brain was working. And then H equals. So solving for H, we divide this through. All the units cross out except for the meters cubed. That just goes to meters. And since it's down below, this ends up down below. The denominator in the denominator flips up to the top. And we're going to be left with meters. 6.7? 6.70. And the units are meters. Oh, lost my. Like 36, 37. Yeah. That is the depth of the alcohol that would need to be maintained. It's good. Okay. I'm going to trust you when you say, yep, we're good. 38 is the last one. When you dive to a depth of 12.5 feet in seawater, what is the pressure? 12.5 feet. Seawater. Pressure equation, specific weight times H. The specific weight of seawater is no idea. Well, let's go to those appendix again. Wasn't there something about seawater? Or was it just water? So we'll go to common fluids again, maybe?
Yep.
Yeah. Seawater. Is this all metric? Yeah, it is, isn't it? Is there another one for, yep, US. Seawater, US. What column is specific weight? This one. Looks like it's 64. Is that what you got?
6.
Is that out of the internet? Okay, that works. I'm going to use 64. It's from the book. 0.00. And the units in the US should be pounds per foot cubed. And we multiply by the height of 12.5 feet. And we end up with 64 and 800. 800 pounds per foot squared. So that's 800 PSF. Pretty unusual unit for pressure underwater kind of thing. Seems huge, right? But remember, that's per square foot. Per square foot. So if we get it to per square inch, we just take the 12 inches per foot. Yep. I'm just writing my units out. Right here, right? 12, 12, 12. And I wrote it this way. Oops, that's wrong, because the 12 is down here. Because I want it to cross. I want the feet to cross. So you write that conversion feet squared on top. That goes away, and it leaves inches squared at the bottom, but it is a 12 squared that we're dividing by. So P is going to be 800 divided by 144, 12 times 12. 5.55 PSI at 12.5 feet. Every square inch, 5 pounds. I mean, it doesn't seem like a lot, but on your body, you have a lot of square inches, and every square inch sees 5 pounds as you go down to 12.5 feet. So per foot, and I have like right here, right? There's a foot in my body right here, square foot, 800 pounds. That's a lot. I mean, you're being squished by a lot of pressure when you go underwater. Fortunately, there's another 800 pounds on my backside, right? That's doing the same thing. So it's doing it everywhere in every direction. So you don't feel this push in a direction. It's an equilibrium push, but it is a squeeze, and it is squeezing you. And you feel it. 12.5 feet, you're going to feel that pressure. And everything shrinks. My whole size gets a little smaller, right? So when you're a diver and you go down to say 60 feet, your weight belt, which was tight when you dropped in, at 60 feet, your weight belt will fall off you because you have been squeezed much smaller, and it'll literally just fall right off your waist. So as you dive and go deeper, you tighten your weight belt. The new modern weight belts actually have elastic and they tighten themselves. But back in the day when I learned, there was no elastic involved. And if you weren't tightening your weight belt, then you're going to lose your weight belt. So yeah, as you dive, you get pressed. It takes all of the gases in your body and compresses those because gas is compressible. Air is compressible, right? We take an air compressor and we compress it. That's what we do with an air compressor. Well, all of your nitrogen and your oxygen in your bloodstream, in your cells, gets compressed. As you dive deeper and deeper, it gets compressed, compressed, compressed as you go down, right? When you come up, those little cells need to expand and get back to their normal size. But if you come up too fast, they can't expand as fast, right? So then they start traveling around not expanded, and all of a sudden they just open up when you get to the top, and they create these clusters of things in your blood called nitrogen narcosis, and that can kill you. So you have to come up as slow as you go down, is the basic rule. You can't just jet to the top. Well, if I'm at 60 feet and my weight belt falls off, guess what? I'm jetting to the top whether I want to or not. So yeah, there's a lot that goes on when you go underwater. And this is only 12.5 feet, not very deep, but it'll pop your ears hard. Yep. Yeah, you get about a minute to get into that chamber and get back down to pressure before it starts taking effect. Yeah, it's nuts. Those guys, that's deep diving. But I was a certified deep diver, probably not anymore because I haven't dove deep. But anything above over 130 feet is a deep dive, and that requires you to come up in certain stages and wait. So from 130 feet, you got to come up to say 80 feet, wait for 5 minutes. So you're suspended right there. You have to have fully control over your ability to stay down. And then at another 60 feet, you got to come up and wait another 5 minutes. Then you can surface out. So if you don't plan your oxygen right, you run out of air because you didn't plan. Yeah. So there's a lot that goes on in deep dives. It's fascinating. It's pretty fun. A deep dive at 130 feet, when you let air out, those bubbles are like glass. They are so compressed. That air is so compressed. When they go up, they hit each other and it's like glass just tinkling off each other. It's creepy. It's creepy as hell. Where normal bubbles, if you go down, it's just like bubble, 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 right? Down at 120, it's like tink, 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 tink. They're so compressed. Yeah, it's very strange. And it's super dark down there. All right, let's turn them in. Cassidy's table is the collector, not Cassidy. Even though she thinks she's the collector, she's not. All right, let's do some chapter 4. Get into the good stuff. We'll spend a little time in this one because it does get complicated. Requires us to remember our statics a little bit. So this is forces due to static fluids. So this is essentially underwater forces. You can think about these kind of things that you go through. I don't know if you've ever been to the aquatic center in Newport. It's super cool. Like they have one of these tunnels where you can go through. So of course, a lot of pressure going on there. What we're going to talk about is surfaces underwater. So any of these kind of tank storage systems has surfaces underwater. You know, a fish tank is a perfect example. When you fill a fish tank with water, there's a certain amount of pressure on the end walls that are trying to blow it open, right? Certain amount of pressure on the side walls that are trying to blow it open. That's the kind of loads that we're trying to calculate, is those loads due to containing fluid or something underwater fluid. For example, this thing, there's some kind of hatch here in this fluid system. There's fluid pressure trying to just blow that hatch open, right? That makes sense. How much pressure is there? Great question. That's what we want to be able to calculate. Any of these kind of things, right? A dam, for example, is essentially a wall that is holding back water, a whole bunch of pressure there, and then there's always going to be a bunch of gate valves or sliding valves that are going to let the water in and out. How much pressure is on those? That's, again, what we want to calculate. All right, so I'm just going to go to this and talk about it because it is, we've done this before in statics, but it just wasn't fluid pressure. So let's go for the fish tank first. Standard fish tank. I'm just going to make this up. So horizontal surfaces underwater are the easiest. Vertical are the next hardest. And then round ones are really difficult. And then ones that are on an angle are a little bit difficult. Not too bad, right? But a fish tank has basically horizontal and vertical surfaces. There's the horizontal surface at the bottom. And we'll do that one first. We got to give this thing a size. And we'll actually put it on like a stand. Right? That makes the fluid pressure worse because there's nothing supporting that bottom. We'll make it 48 inches by 24 inches, and we'll give it a water depth of 20 inches. I'll give you time to draw. So we'll do horizontal and vertical today. And then we'll do incline and round. Maybe just incline on Wednesday. Everybody got it? 48 by 24? All right. 20 inches deep. And we'll make it a saltwater tank. The saltwater fish are cool. And we'll go with a specific weight of 64 pounds per foot cubed. All right, so the first thing we need to know is the pressure on the bottom. Like, you need to know the depth that you're working with, 20 inches, and then how much pressure is on the bottom. And let's get that in PSI, pounds per square inch. What was the pressure formula? Specific weight times H. All right, I'll give you a couple minutes to get that. In PSI. So should be pressure equals 64.0 pounds per foot cubed. And our height is 20 inches, so we need that converted by 12 inches per foot, right? And we're left with, what'd you get? Be 100. Oh, that's going to be foot cubed. Yeah. So here, let me do that differently. We want it in PSI, right? I'm just going to leave that 12 inches that way and convert that to 12 inches cubed per foot cubed. And that will cross. So that'll give me pounds per inch squared. .7407 PSI. Anybody get that? It is. I did cube it.
Yeah.
But you're correct. The 12 should be cubed. .7407 pounds per inch squared. So if I'm doing an analysis of this bottom piece, then if I draw that bottom piece kind of in this front view, right, then it just becomes like this straight line. So this is the front view. And I'm just doing the bottom piece. It does have sidewalls here, but I don't care about that right now. I'm just doing the analysis of the bottom piece. Okay. So for every square inch, or every inch along here, I get 0.7407 pounds, right? So as I look at this bottom piece, I can draw the pressure curve. It looks something like this. It's going to be consistent because it's the same. Right? So for every square inch, there's 0.7407. So how many square inches do we have in depth away from my view? We have 24 inches, right? There's 24 inches here. So here's my front view, looking at it from here. I know I have this like load, this distribution. In statics, we called it a distributed load. But it also goes away from me 24 inches. So since there's 24 of them, I can take the 24 times 0.74. And that's 17.7 pounds, 0.777 pounds per inch in this direction, because I multiplied by 24 in the depth direction, right? So I accounted for all these 24, but I haven't really accounted for the 48 yet. Everyone kind of see that? It's like we're looking deep into the fang. And since there's 24 inches in that depth, I multiply the 24 times 0.74 and I get the per inch load looking at the front view. So for every inch, 17.77 pounds. That becomes my distribution. In statics, we use this, it's called a line distribution. It's pounds per inch because they're just in a line here. We've already accounted for the depth. If I looked at it three-dimensionally, it would look like this, right? That pressure would be just throughout the thing. Yep. And that was the 0.7 was these little guys. But now I count for the 24, I get to 17.77 pounds per inch. Okay. So that's the distributed load. Like if we were going to calculate deflection or bending stress or any of those kind of things, we would use this distributed load. Because that's what it's feeling. It's feeling this it's not feeling a concentrated load. It's not all in one spot, right? It's nicely distributed. That's what fluid does. So this is what we would use. If we wanted to know the total load, then we would need to concentrate the distribution. The concentrated load, if you don't remember, would go directly through the center, and it would be the 17 times the 48. 853 853.33 pounds. So if you don't know fish tanks, they're flipping heavy, especially when they have water in them. This is a big fish tank. 48 is like this big. 24 is like, this is a big fish tank, like what you would see in your medical office or a dentist's office kind of thing, right? 853 pounds of fluid weight. It's a lot. But even the 17.77 pounds per inch, every little inch, 17 pounds, that's a bunch of distribution. So that's definitely going to take and create some bending stress on that bottom surface. Horizontal is easiest because it makes this kind of curve, a rectangle, which is the easiest load curve to deal with, a rectangle. Does that make sense? Not too bad. Let's bring back some statics because we have to deal with distributions. And if we wanted to carry this out to complete the problem, then we'd have to come up with like a bending stress, right? Glass doesn't bend real well, so we want to make sure the glass is thick enough and that it can handle that kind of distribution. All right, let's do a vertical surface. We'll do this side surface. So that's the bottom. This analysis is the bottom. There's the big side, that would be a different analysis. And then there's the little side, that would be a different analysis. So we'll do this little side, the 24 by 20 height. We already know the pressure at the bottom. That stays the same, right? So pressure at the bottom, 0.7407. I'm going to draw that side surface, blow it up a little bit. And I'm just going to say it's 20, even though here, I'll make the glass go a little further. So here's where the water is, right? And I know the pressure at the bottom, and I'm going to draw that pressure big, is 0.7407 pounds per inch square. Right, and that's what we calculated, correct? Yeah? All right. That's at the bottom. What's the pressure at the top of the water? The water pressure at the very top surface. What would the pressure be right here? It's zero. There is no water pressure at the top, right? Nowhere up here. All this, the whole area up there is zero. So if I'm drawing a graph, I have a bunch of pressure at the bottom, and I have zero pressure. And we're always talking gauge pressure here, which means we're just ignoring the atmosphere. Atmospheric pressure, the pressure we're existing in is zero, right? When you're talking gauge pressure. Because a gauge, if you had it here, it would be reading zero. like nothing on it. So clearly that creates a different load curve, right? The pressure at these different elevations just gets smaller and smaller and smaller. I could calculate the pressure at any of those places, but I don't really need to because I calculated the pressure at the bottom and I know it's a straight line slope. With the pressure at the bottom being this, now I want to account for the depth. So how deep of a sidewall was it? Because I'm looking at it again from the front view. It goes 24 inches deep, correct? Just like this one did. This one, looking at it from the side, is 24 inches this way. It's 20 tall by 24. So the same kind of maneuver to get this to what we call a line load is going to be 24 times this pressure. So we have that number too, because I think we did that on the other one, right? 17.777. So 17.7777 pounds per inch. It's called a line distribution because it's per inch of that depth. So then if I wanted to know the total side load on that side, how do I get it? Same way I got it here. This was a rectangle. So I calculated the area of a rectangle. The load curve was a rectangle. What's my load curve now? Or a triangle. What was that? 1/2 base times height, and it does not matter what you use for the base and the height because it's a multiplication. But we do want to use this 17.77 pounds per inch as our load at the bottom. So 1/2, the base is 17.777 pounds per inch. I'm going to make sure I put the units in here. And then how tall is my rectangle or my triangle? 20 inches. And those inches should cross out and you should be just left with pounds. So this would be like force total. I get 177.777. That's this, F, the concentrated load of the distribution. Where does that get applied? Yep, geometric center of the load curve. So our first load curve was a rectangle. That was easy, just goes in the center. Whatever your load curve is, it goes in the geometric center. So it goes here, which is 2/3 from the pointy end, or 1/3 from the 90. So if I wanted to know how far up the fish tank is, the total load would be applied, it's 1/3 of 20, which is 6.666 inches. Now I have everything I need to do an analysis of the sidewall, right? I know how much load's on it, 177 pounds, 177.7. It's a bunch. It's not as much as the 853 on the bottom, but 177 on a side, trying to blow that side out. It's a lot. If this has a little metal frame to it, like a lot of them do have these little metal side frames to them, right? Then that little metal side frame is going to have to be able to carry that kind of load. So if we were to design it or go for the design, we'd have to know how much load's on it. So big tank, right? Just like we had. And if you have some kind of sloped straight line surface, you know, some kind of, I don't know, viewport or something inside there. Same kind of system, we have to figure out the load curve on it, right? And since this has a different H value than this, then there's a different pressure here. Water pressure always works perpendicular to a surface. So larger pressure here, I'm going to kind of draw it at a weird angle. Smaller pressure here. So I have a bigger, right? And then the load curve is going to look something like this. And this goes all along here on every piece of it. Then it creates some kind of trapezoid. Wow, that's really hurting my head to look at it. Right? But the load on the thing is going to be all over it and then slightly gets bigger, becomes some kind of trapezoidal load curve when you have an angle. So that obviously gets more complicated. When you have a round, maybe there's some kind of a round surface here and this corner is gone. Then you have pressures here that are perpendicular and they go perpendicular to the surface all the way around. That becomes your load curve. Challenging. With this being a smaller pressure, this being a larger pressure, because these H distances are different, right? Whenever your H distance changes, then your pressure changes. Your load curve changes. So we'll do these Wednesday. Your homework is, wrote it down somewhere. Out of chapter 4, 11 and 12. Out of chapter 4, number 11, 12. There you go. And we did election. I'm a little behind on all my course management. That happened at 8:30. All right, any lingering questions about that? I think we should look at it. Let's make sure those are good problems to work. 11 and 12, is that what I said? Yeah. I think they both have pictures is what I tried to give you. Calculate the total force on the bottom of the closed tank shown in P411. So that's this one. Calculate the total force. So that means the concentrated load on the bottom, total force. So that's just like what we just did. Perfect. 12. If the length of the tank, is 1 point, calculate the total force on the bottom of the tank. Ah, a little different. And 2 fluids. So that'll help hurt your head a little bit. So we'll let you struggle with that. Just those two. All right. We're done. Nice job. Week 3, just like that.